Hi everyone. We're continuing with our discussion of the central limit theorem, the CLT, for sums and more importantly, for averages or means. We left off last time with talking about this relative frequency histogram, or spike plot in this case, for the values of x bar, a sample mean. In the case where x bar is the average of a pair of dice when a student rolls a pair of dice. Remember, back here, tables of sums versus means. What was the probability of getting various sums on a pair of dice? The probability of getting a 2 was 1 out of 36. There were 36 cells in here. The probability of getting a sum of 2 on this pair of dice was 1 over 36. The probability of getting a 3 was 2 over 36. Don't worry about simplifying. The probability of 4 was 3 over 36. The probability of 5 was 4 over 36. P of 6 was 5 over 36. P of 7 was 6 over 36, or 1/6. This is the most likely probability. 7 is most likely as a sum. But then the probabilities go down symmetrically. P of 8, we're back to 5 over 36. P of 9 was 4 over 36. P of 10 was 3 over 36. P of 11 was 2 over 36. P of 12 was 1 over 36. So if you do a probability histogram, or in this case a spike plot, you would get this spike plot here, this triangular spike plot, going from 2 through 12, using this summation x as your axis. The sum or total of the two dice can be somewhere between 2 and 12, and 7 was most likely. For a triangular distribution like this, the central value is the most likely value. Now, let's say that instead of the sum, we consider the average on the two dice. The average can be between 1 and 6. Again, we could roll 2 million dice, and we know the average will be between 1 and 6. Well, we looked at this table of averages. And basically, we get the same kind of distribution as before, except that the distribution is going from 1 to 6, not 2 to 12. But it's the same shape distribution. The probabilities go up steadily, then down symmetrically. So this spike plot as a shape applies also to the x bar distribution, but the scale is going not from 2 to 12, but from 1 to 6. The most likely average is 3.5. Again, for a triangular distribution, that central value, the mean of this x bar distribution, 3.5, is also the most likely value for the mean. That's not always the case, but for a triangular distribution like this, the 3.5 here, the mean of the means, the expected value of the sample mean distribution, will in fact be the central value and the most likely value. Again, why is it triangular? The probability here for the sum or this average, it's 1 over 36, then 2 over 36, 3 over 36, 4 over 36, 5 over 36, 6 over 36, or 1/6, the most likely. Sum 7, or average 3.5, then down 5 over 36, 4 over 36, 3 over 36, 2 over 36, 1 over 36. Again, looking at the 3.5, we can say that the mean of the means, denoted by mu sub x bar, that's the mean of the x bar distribution, the distribution of sample means. I'll explain this more later on. The mean of means is 3.5. It's the same as the Big Daddy mean for the original Big Daddy flat distribution. Mu is also 3.5 over here. And that's no coincidence. Okay, so let's talk more about this idea of sampling, because we can refer to this as both a probability distribution for x bar and also a sampling distribution for x bar. It's the same thing. The idea is if you take many samples, like if you have 1 million students or 1 billion students, then the sampling distribution will very closely resemble this actual theoretical probability distribution. What's the idea there? Okay, once again, here's our Big Daddy distribution for one die. X is the result when you roll one die. I don't care what color it is. X is the result when you roll one die. We don't know it yet, but we do know its probability distribution. We don't know its value yet, whether it's 1, 2, 3, 4, 5, or 6, but we do know from the outset the probability distribution. We assume it's a discrete uniform distribution on the integers from 1 through 6. Let's call this Big Daddy distribution D. Later on, D might represent some other distribution, but for right now, this is our Big Daddy distribution D, this discrete uniform distribution, the result on rolling one die. Now let's say a student takes a red die and a green die, two dice, and rolls them. X sub 1 will be the result on the red die. X sub 2 will be the result on the green die. Right now, I don't know them yet. They're random variables, but they each have this distribution. X bar, the sample mean, is also a random variable. I won't know the value of this yet until I get values for x1 and x2. But I do know that whatever happens, to get the value for x bar, I'm going to add these two values up and divide by 2. Now, even though x has D, this flat distribution, as its Big Daddy distribution, the distribution for x bar is not flat. It's triangular. I'll go up. It's triangular. It was this over here, using this blue scale as the scale for x bar, the sample means. Again, x bar has a triangular distribution up here, this guy here, using the bottom scale, the blue scale. All right, so let's talk about some samples. Let's say that we have a big lecture hall of 1,000 students. Don't laugh. Very often in big colleges, you'll have a lecture hall of 1,000 students. That'll be in the hopefully near future when we get back on campus. Imagine 1,000 students, each rolling a pair of dice, maybe a red die and a green die. Basically, each student is taking a sample of size 2 from this Big Daddy distribution over here. Each person takes a sample of size little n equals 2 from D, the original uniform distribution. And then each person finds the sample mean of the 2 dice that that person rolls. And then these values here will be the values for x bar, the sample means. So for example, for student number 1 rolls a red die and a green die. And let's say that for student 1, for sample number 1, the result on the red die is 2, the result on the green die is 3. Then the sample mean, the result of the sample mean for student number 1 is 2.5, the average of 2 and 3. For student number 2 gives us sample number 2. Let's say a 6 on red and a 2 on green. That means that that student's average was 4.0. And so forth. We go through all the students. It may take some time, or maybe they're all doing it simultaneously and they're entering data on their iPhones. But student number 1,000, let's say, gets a 1 on red, a 5 on green. That student's average is 3.0. Okay, and let's say that we take these 1,000 sample means and we do a spike plot for them, a relative frequency distribution. I claim that the spike plot for the relative frequency distribution for these sample means will very closely resemble this triangular plot over here. Granted, we may have sampling error. Remember, when we were doing sums of dice in our class, we had what, about 25, 30 students or so. We got a fair bit of sampling error, but it was very roughly triangular, very roughly. All right, but with 1,000 students, it'll look much more closely, precisely triangular. With 1,000,000 students, it looked very close to this triangle over here, this triangular distribution with this scale in blue. Okay, that's why I have this in blue over here. All right, so once again, the relative frequency histogram or spike plot for the values of x bar, the sample mean random variable, which varies from student to student in value, should resemble this triangular distribution. And that's because of the law of large numbers, the LLN. The idea that if you have many, many samples, then when you analyze the results from many, many samples, then you're going to get something very close to this probability distribution. In other words, the sampling distribution will be very close to the probability distribution. The distribution from a whole bunch of samples, like a million samples, will be very close to the distribution you get from theoretical probability. All right. Now, I claim that the sampling or probability distribution for x bar has, as its mean, the notation is mu sub x bar, the mean of the x bar distribution, but it's the same as the Big Daddy mean, mu, which is 3.5. Now remember, all the way back up here, right, we had the result on one die. It had this probability distribution, a discrete uniform. Mu for this Big Daddy distribution was 3.5. Okay, right here, 3.5 was the mean of the Big Daddy distribution. And it's also the mean for this over here, right? Here was 3.5 over here for x bar. The most likely average is 3.5 for this triangular distribution. It's at the center. Again, for a triangular distribution, the central value is the most likely one. It's not always the case that the central value is most likely. You could have a messed up distribution like this, for example. But for a triangular distribution, yeah, the most likely guy is in the center, 3.5. So it's not surprising that the mean of the x bar distribution is the same as the original mean. So whether you're rolling one die or two dice or 2 million dice, then the expected value of the sample mean, that is the value that the sample means will tend to center around, the value that the sample means from the samples will tend to center around, will be 3.5. Whether it's one die, two dice, or 2 million dice, the center will be 3.5. In practice, if you have a million samples, it'll be very close to 3.5. Now, all the way for one die, I told you that the standard deviation for the flat top distribution for one die, sigma was about 1.7. It was about this over here. And this was based on the optional handwritten formulas and calculations from lesson 16. So you didn't have to know how to figure this out. Just take this on faith. That sigma was about 1.7 for this original distribution. But that's not the measure of spread for the new x bar distribution. So even though the mean for the x bar distribution is the same as the Big Daddy mean for the original distribution, 3.5 here, it is not true that sigma for the x bar distribution will be the same as sigma before. Now, the standard deviation of the x bar distribution, the distribution of sample means, that's called the standard error. The standard error, or SE. But again, it's the standard deviation of the x bar distribution. These terms are interchangeable if you're referring to the x bar distribution. Now, this formula for standard error, the standard dev for the x bar distribution, it's not just sigma, the way that this was just mu. It's not just sigma. It's sigma over the square root of n. So to compute the standard dev for the x bar distribution, the standard error, you take 1.7078 sigma for the Big Daddy distribution for one die, and you divide by the square root of the sample size, which was 2 in this case. Each student is rolling each student is rolling 2 dice. Each student has a sample size of 2. That's different from the number of samples. We're talking about the sample size, the number of dice that's rolled by each student. 1.7078 divided by the square root of 2 is about 1.2076. And this is going to be the standard deviation of the x bar distribution, or the standard error. The standard error. This will always be less than that. It will always be less than the Big Daddy standard deviation. And why is that? Because as you roll more and more dice, as you go from 1 die to 2 dice to 4 dice to 2 million dice, then the distribution of averages will be more tightly clustered around the 3.5. So you're going to get less spread. As n increases, as the sample size, the number of dice increases, 2 dice, 4 dice, 8 dice, 2 million dice, that's going to have a lowering impact on the standard error, and this will become a lower and lower number. It's going to go down. As n approaches infinity, this whole thing approaches 0. We're going to get very tight clustering around the 3.5 as n gets bigger and bigger and bigger. We'll talk about this more in the next lesson.